All right, so we're going to take a look at lesson 4, number 3F. And in that case there, they asked us to find the rate of change function, which we now know is called the derivative for this function here. Okay, so what we're going to do is take the limit as h approaches 0 of f at x plus h minus f at x all over h, remembering that now we're keeping the x value variable so that we can come up with a function that gives us the rate of change of x to the 3/2 at any point we like, just any x value. All right, so first thing as usual, let's put this in. And what do we have? So we've got x plus h to the 3/2, okay, and then minus x to the 3/2 all over h. All right. Now, the problem with trying to work with this expression here, this is just a single power, so not really much to do, but you can't expand this, or you could think of expanding it when you remember what the exponent 3/2 means, okay? So let's, on the side, just remember what the exponent 3/2 means. So if I have a to the 3/2, okay, there's two ways of looking at that. I can write that as the square root of a cubed, or I can write that as the square root of a all cubed, okay? And the reason being is that you can split this up as 3 times 1/2. So first you're cubing and then you take the square root, or you can split it up as 1/2 times 3. So first you're taking the square root and cubing. And the reason why I bring this up is that I've got this x that I want to be able to operate with, but it's stuck inside essentially a square root. Okay, so my strategy here is to use the trick we often use when we've got two terms involving square roots, is I'm going to multiply by the conjugate. Okay, so are there any questions as to why I'm going to use the same strategy as with a square root? Because essentially this exponent contains in it a square root. Any questions on that? No? Okay, so let me go ahead and do that. Now, notice I'm not going to bother writing it in square root notation. Okay, I might as well just keep it as 3/2 because I've also got this 3 here. But remember that the denominator portion represents this square root. Okay, so I'm just going to do what I normally do, multiply by the conjugate. And of course, if I do anything to the numerator, multiply anything to the numerator, I got to do the same thing to the denominator. Okay. Okay, now because I've got these conjugates being multiplied, I know that the middle terms are still going to cancel out. So it's still going to accomplish that portion of it, but it's also going to accomplish the goal of getting rid of the square root, because when I multiply x plus h to the 3/2 times x plus h to the 3/2, well, these are the same base. I'm multiplying so I can add the exponents. And what is 3 over 2 plus 3 over 2? It's 6 over 2, or 3. So that just becomes x plus h cubed. All right. And so this now becomes something that I can actually work with. And then here, when I multiply x to the 3/2 times x to the 3/2, same thing, 2 powers with the same base, I can add the exponents. So this is going to be minus x cubed. Okay, and then of course in the denominator, I also have this big ugly expressions, x plus h to the 3/2, okay, plus x to the 3/2, but I'm not going to worry about that till later, because one thing you'll notice is h approaching 0 doesn't make this portion of it approach 0. So as usual, I'm going to try to eliminate that h in the denominator. Okay, so any questions so far? No? Okay, so now I just got to grind this out. So here, well, we've done this before. If you look back at one of the previous ones, you'll see that we've, expanded x plus h all cubed. So I'm just going to write it out. All right, so let's see what we have here. We have x cubed. Okay, or does somebody want me to actually multiply this out? No, okay. So here we're gonna have we're gonna have x cubed plus we're gonna have 3hx squared plus 3h squared x plus h cubed. So if you were to multiply x plus h times x plus h times x plus h, you would get this, and then here minus the x cubed all over h times this expression. And as we see often happens, the terms that don't have an h in them just cancel out. And then we realize that all the terms that are left all have a factor of h. Okay, so now I can factor out an h in the numerator, and let's see what we're left with. Well, we're left with 3x squared. Okay, and then here plus 3hx plus h squared. And then just write all this out. And we have exactly what we were hoping for. Okay, the h's cancel out. And now I have something that I can evaluate as h approaches 0. Okay, so let's see what happens. These two terms are both approaching 0, so they're gone. The only thing that's left is the 3x squared, because regardless of what the value of x is, it's not affected by h approaching 0. So we got 3x squared left in the numerator, and let's see what we have left in the denominator. So here, as h approaches 0, this thing inside the bracket approaches x. So we've got x to the 3/2. And here, this has no h. It's unaffected by h approaching 0. So another x to the 3/2. And now we can just simplify. Okay, so 3x squared. And this is going to be, well, it's the same term being added. So 2 times x to the 3/2. Okay, and what are we left with? Well, this is just some constant, 3 over 2. And here we can simplify this further because we're dividing 2 powers with the same base. Hence, we can subtract these exponents, and 2 minus 1.5 is just 0.5 or 1/2. All right. And we finally get, after all this algebra, a fairly simple function that's going to give us the rates of change or slopes of tangents for any point on this curve here. Okay. Now, I'm not going to talk about this right away, but hopefully one of the things you looked at was to see if there were any patterns, because I do want to remind you that this was a lot of work to find the derivative of this one particular function. You know, as soon as I have x to the 3/2 plus x, say, I'd have to start all over. And maybe that algebra wouldn't be quite so straightforward. There's a lot of writing, but the algebra is fairly straightforward. Okay, so this is why I'm hoping that you're going to take it a little further and find some patterns. All right, any questions? I don't remember who asked this one. Any questions on this? Okay, so again, we see that when we're using this limit definition, we really have to be careful with all our algebra, because you miss one little sign somewhere and you might not have things reducing as they need to. All right, so if there's no questions, I'll move on to the next one. So page 193, number 16. Okay. All right, let me just find that in the textbook. Okay, so here, let me show it. It's a little on the long side. So let's see what it's asking to do. It says, to understand why we cannot work with the symbol infinity as though it was a real number, they're asking us to consider these two functions here. All right. So, if you think of this one here, the numerator and denominator are both approaching infinity. Okay. So But does that mean we can just divide? Infinity divided by infinity, you know, if you treat it like a number, it would just be 1, which of course may or may not be the case. Okay, and then here, if I were to subtract two things that are approaching infinity, so in this case, you know, we're going to be showing that both f of x and g of x approach infinity. When I subtract infinity minus infinity, if we treat infinity as a number, you would expect the answer to be 0. But here, apparently, the answer is not going to be 0. So this is what we have to show. Okay, so essentially, we're going to be confirming, using this counterexample, that you can't just treat infinity like it was, you know, the number 7. All right, so let's start with A here. Actually, let me write down the functions. So we have f at x is equal to x squared plus 1 over x plus 1. And g of x is equal to x squared plus 2x plus 1 all over x plus 1. Okay, and here it says in A, show that these functions both approach infinity. All right, now what we can do here is we can do this 2 ways. Now, I guess I'm going to be making this possibly longer than I would expect, but let's kind of do it the intuitive way. And then maybe let's go out on a limb and do it a little more algebraically. So what do we know about rational functions where the numerator has a higher degree than the denominator? Who's going to tell me what we know about these types of functions? Anybody? Well, what we know is that when the numerator has a higher degree, we know that the functions are going to approach positive and negative infinity. Now, we're only interested in the limit as x approaches positive infinity. And when the x values are positive and big, these are both going to be positive. So we know it's going to have to, you know, if you look at numerator and denominator, it's going to have to approach positive infinity. So here we can say, since the degree of the numerator is greater than the degree of the denominator, okay, we can say that the function approaches positive infinity as numerator and denominator are both positive as x approaches positive infinity. Okay, because here I'm taking a positive number, squaring it and adding 1. Here I have a positive number adding 1. Here, positive numbers all being added together, positive numbers all being added together. So I know it's going to positive infinity and not negative infinity. So this is the intuitive approach, because this is what we found last semester, that as soon as the numerator is a higher degree. If we want the more formal approach, well, we would actually show, like we did last semester, why this is the case. Okay, so G is actually, I'd say, a little easier, because the limit as x approaches positive infinity of g of x, well, hey, look at this. You can factor the numerator. It's a perfect square. So x plus 1 squared over x plus 1. So one of those cancels out with the one in the denominator. So now I've got the limit as x approaches positive infinity of x plus 1. And this is clearly getting very, very large and positive. Okay. Now, this one here can't be factored. Does anybody want to tell me what I would have to do to show formally that it was approaching positive infinity? Does anybody remember what our reasoning was, our algebraic reasoning? Any takers on this one? No? Oh, well, okay. Well then, you know, do a little review here. What we would have done is we would have divided these two functions. So 1, 0, 1 divided by, that represents x squared plus 1. And then negative 1 represents x plus 1. and I would do division. So this becomes 1, this is -1. So add these together, -1, and then -1 times -1 is 1. And so what we have is that when we're finding the limit of f at x, we can rewrite this function here as the quotient, which is x minus 1, plus the remainder over the divisor. And now we see very clearly that this portion is approaching 0. And so this whole thing is just going to be approaching positive infinity, because that's what the function x minus 1 approaches. Okay, so intuitive and formal way, okay, based on our results from last year. The more formal way, where we're actually showing why both of the functions are approaching positive infinity with algebraic means. The only difference here is I'm now using the limit notation. Any questions on this portion? No? Okay. So if we go to B, and we're taking the limit as x approaches positive infinity of f at x, minus g of x. Again, these functions are both approaching infinity. Like I said before, if we assumed we could treat infinity like a number, it would just be approaching 0. But this is apparently not what happens. So let's see if we can figure out what happens here. Okay, so f at x is x squared plus 1 over x plus 1. Okay, and this is minus x squared plus 2x plus 1 over x plus 1. And so now what I'm going to do is I'm going to do some algebra, as we do when we're uncertain about what a limit may or may not approach. Okay, and we're kind of lucky because the denominators are the same. So here, this is where we have to be careful that when we bring this under a single fraction, that it's x squared plus 1 minus, and make sure you're putting, brackets there. Okay, and let's keep simplifying. Okay, so here you have x squared minus x squared is gone. So it looks like here you have negative 2x. Okay, negative of positive 2x, negative 2x. And then here you have 1 minus 1. That also disappears. Okay, so this is what we're left with. All right. And so now, once we look at this expression here, what does this type of function approach? Well, as we saw last semester, since we've got two polynomials with the same degree, this is just going to approach the quotient of the two leading terms. And the quotient of the two leading terms here would just be -2. But of course, what is -2 not equal to? It is not equal to 0. Okay, so here, well, this is where we can conjecture that infinity minus infinity is not necessarily equal to 0. Okay, and of course, keep in mind, these are not actual numbers, but even if we have limits where both functions are approaching infinity, the subtraction of those two functions don't necessarily approach 0. In this case here, they in fact seem to be approaching -2. All right. So I'm not sure who asked that question. Any details you need?
Wait, what does like not equal to 0? Like, what does that like mean?
So this means that if I subtract two functions that both approach infinity, that both approach positive infinity, and say here I should have called them f and g, then f minus g does not necessarily approach 0. Okay, that's what this is saying. Okay, so I'm using notation here to show, but essentially this is saying that just because two functions are both approaching infinity, it doesn't mean that their difference is going to approach 0. Okay, it could be that it does, but this shows here that there's no guarantee. And, conclusion to that is you can't just treat infinity like some number. Okay, does that answer the question?
Yeah, thank you.
Okay, great. All right, anything else on this one here? Otherwise, somebody's asking for 17 from some other page. No, okay. So in fact, 17 is a really good question to ask, because one of the things another person asked me to do is a limit that involves an absolute value. Okay, and I believe, if I'm not mistaken, that's one of them. So page 53, just get new paper. So it's page 53, number 17. And here they give us this function, which is defined as x times absolute value of x minus 1 if x is not equal to 1. And then it's defined as 0 if x is equal to 1. Okay, and then it says evaluate the limit of g, not surprisingly, as x approaches 1 from the right and as x approaches 1 from the left, and then determine whether the limit exists. So obviously, if the right-handed, left-handed limits are equal, it exists. If not, it doesn't exist. So can we see here that in terms of A, this second statement is of no interest to me? Okay, because what I'm interested in is the limit as x approaches 1. So I'm only interested in the numbers to the right of left of 1 and to the right of 1. This is of no consequence to me in part A. However, it would be in part B when they ask you to graph it. Okay, but because I want to approach, so what we're looking for in A is the limit as x approaches 1 from the left. Oops, g of x, and the limit as x approaches 1 from the right of g of x. And this is where we come up to a little bit of a problem, is that to the left and right of 1, this function behaves differently, because to the right of 1, x minus 1 is positive, and to the left of 1, x minus 1 is negative. So as we've done many times, I'm going to actually write this using 3 expressions, this function here. Okay, so this is kind of the first time we see that. A piecewise function that has to be split up into even more pieces. Okay, so this is not going to change, 0 if x is equal to 1. But what we are going to be looking at is, what does it look like when x is less than 1 and when x is greater than 1? Because that's when the expression inside the absolute value changes. All right. So, and I just realized there's a missing x minus 1 there, okay, in the denominator. So notice here, I don't have an equal sign on either of these. That's taken care of by that third statement. So let's see what happens to the left of 1. When x is less than 1, okay, x minus 1 is negative. So that means I can replace absolute value of x minus 1 by the negative of x minus 1. Okay, so are there any questions on this? So forget this x here, just look at the absolute value. Here we're assuming x is less than 1. So we know the number inside that absolute value is negative. So I multiply it by -1 to ensure that it's positive. Okay. Any questions on that? Okay. So now when I'm looking at x greater than, oops, sorry, not 0, that should be 1. Okay. When x is greater than 1, this thing inside the absolute value is automatically positive. So it's just going to be equal to whatever that number is, x minus 1. And here we see that we can simplify this further, okay? Because now, and this is the reason, one of the reasons for putting it as a piecewise function is that now we can do some algebra. We see that in the numerator, there's a factor of x minus 1, and the denominator is a factor of x minus 1. We can reduce those, and what are we left with? Just negative x when x is less than 1. Here, same thing. There's a factor of x minus 1 in the numerator, factor of x minus 1 in the denominator. So this is now just going to be equal to x if x is greater than 1, and it's 0 if x is equal to 1. Okay, now you might be seeing already where this is going, because if I take the limit as x approaches 1 from the left, now I'm interested in the portion of the function which deals with values less than 1, which would be negative x. And what does this approach? Well, this is just going to approach, this is just a linear function, polynomial, continuous, so the limit is equal to its function value, so that's just going to be -1. Whereas when I look at the right, I'm now interested only in those y values for which x is positive. So I'm going to be taking the limit as x approaches 1 from the right of x, and this is going to approach 1. And so we see here that because these are not equal, okay, limit as x approaches 1 of g of x does not exist because it's not approaching the same value. Okay. The graph, you can do that on your own or graph that on Desmos if you need to, because essentially, to the left of 1, it's just going to be -1. Okay, actually, let's just graph it real quickly. Okay, so here, this is the value we're interested in at 1. So everywhere to the left of 1, it's equal to -x. So here, try to draw this nicely here. Okay, and I'm going to put a hole there. Okay, then to the right of 1, it's the function x. So here, so let's put 1, -1. It's going to look like something like this. And we'll put a hole there. And at 1, it's equal to 0. So this is what the function would look like. It's like -x. At 1, it's defined as 0. And then to the right of 1, it's defined as x. Okay. And clearly there's a discontinuity at 1. All right. Any questions on this here in terms of the format or in terms of the work that needs to be shown? So I rewrote it as a piecewise function using my knowledge of absolute value so that I could now take the right-handed and left-handed limits at 1, and from there to realize that the limit did not exist. All right, any questions? No, okay. So is there anything else from the people who are online? Otherwise, I had one question that was sent to me earlier by email. No, okay, so I'll do those, and I'm going to do them all at once because they're all kind of similar here, and they're all from page 193. So the first one is 3D. All right, so let's take a look at 3D, which says evaluate the limits as x goes to positive and negative infinity of the function, which I'll give in a second. Okay, so here f at x is equal to 2x to the 5th minus 3x squared plus 5 over 3x to the 4th plus 5x minus 4. Okay, and what we want to do is we want to find the limit as x goes to positive and the limit as x goes to negative infinity. Okay, so the first thing I notice is I have a 5th degree polynomial over a 4th degree polynomial, so I know that it's approaching positive or negative infinity. Now we're going to want to determine whether it is positive or negative infinity. And I also know that because this is 1 bigger than the denominator, it's going to be approaching a line. Okay. Now, in order to find this line, well, I'm going to have to divide these two equations. Okay. But remember here, though, I'm not looking to graph this function. I'm just looking to figure out whether it's approaching positive or negative infinity. So I'm going to try to make my life a little easier here. Is the only thing I need to determine is whether the slope of the oblique asymptote is positive or negative. Because if the slope of the oblique asymptote is positive, I know it's going from negative infinity to positive infinity. And if it's negative, it's going in the other direction. So I'm not actually going to do, because I see this here, I'm going to have to use long division, and I'm not particularly interested in doing that. But if I were to divide these, 2x to the 5th plus blah, 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 and I would be dividing that by, 3x to the 4th plus blah, blah, blah. Okay, I realize that what I would have to multiply to 3 to get 2, okay, would just be some positive number. Okay, so since I know that when I do that division, okay, the first term will be positive, and since that first term is the slope, I know that the slope is going to be positive. Okay, so you see how I'm using only the part that I need in order to determine my result. Okay, so here, because of that, the limit as x approaches positive infinity of f at x. So remember, since the slope is positive, it means the oblique asymptote looks something like this. That means that that's going to be positive infinity, whereas the limit as x approaches negative infinity of f at x. Since the oblique asymptote, again, has that positive slope, to the left-hand side, it's going to be approaching negative infinity. Okay? So you see how here I focused in on only the thing that I needed to determine whether it was going to positive or negative infinity. And so all I needed was whether the first term in my division was going to be positive or negative. And in this case here, positive, meaning positive slope for my quotient, meaning this behavior. Any questions on how I was able to simplify the amount of algebra I had to actually do here? No? Okay, so let's move on to, next one is 5b. And 5b says, for each of the following, determine the equation of any horizontal asymptotes and state whether the curve approaches the asymptote from above or below. So here, I forgot which one was 5b. So that is f at x equals 2x over x squared minus 1 So we know that if we're looking for horizontal asymptotes, in this case here, the horizontal asymptote is given by 0, okay, since the degree of the denominator is the bigger one this time, okay. So if I'm looking at the limit, I'm going to look at the limit of x approaches positive infinity, okay, and then I'll take a look at the limit as x approaches negative infinity. I know these are both going to approach 0, but they want a little more. Is it approaching 0 from above or below? Okay. And this is where I'm going to use, my old trick for determining the sign of the function. So I know that this function here has an x-intercept at 0. If I factor this, x plus 1, x minus 1 has vertical asymptotes at -1 and +1. And remember what we determined back in advanced functions. We said that if these are the only places it could change sign, all I have to do is test one number in the interval from 1 to positive infinity. And if it's positive, it's got to be positive everywhere. If it's negative, it's going to have to be negative everywhere. So all I have to do is test one number. Let's test 2. And what do we have? 2 times 2 is 4, positive, over this is going to be 4 minus 1, positive. So that means that everywhere greater than 1, as I approach positive infinity, the function values are always positive. So it's going to have to approach 0 from the top side, from the positive side. Okay. Whereas, let's do the same thing on that side. Let's stick in a -2. So 2 times -2 is negative, but -2 squared is 4, minus 1 is positive. So that means to the left of -1, it's always negative. So that means it must be approaching 0 from the negative side in that question there. Okay. So you see here how I'm recycling not only my old notation, but our old tricks for determining the sign of a rational function. Okay. Any questions on that? Nope. Okay. The last one that was asked was 9C. Hopefully I'll have enough room there. So 9C, let's see what's going on for 9C. It says for each function, determine any vertical or horizontal asymptotes and describe its behavior on each side of any vertical asymptotes. So notice here, horizontal asymptotes are just asking if there are any. They're not asking us to say if it's approaching from top or below. So 9C, let me just write that down. H at x is equal to x squared plus x minus 6 over x squared minus 4. And of course, it would be tempting to say that there's 2 vertical asymptotes. So I know the horizontal asymptote. That I can say right off the bat. The horizontal asymptote is, y equals 1, because it's a quadratic over a quadratic. I just have to look at the quotient of the leading coefficients. So here I could say the limit as x approaches positive or negative infinity of h of x is just going to be 1. So that's nice and easy. But for the vertical asymptotes, I know I need to be careful with anything where the denominator is equal to 0, because I better check to see if there's anything that's going to reduce. So let me factor this. So this is going to be x plus 3 times x minus 2, because -2 plus 3 plus 1 over x plus 2, x minus 2. And we see that indeed there is going to be a hole with this function. Now, they're not interested in what's happening near the hole. They are only interested in what's happening at the vertical asymptote. Okay, so here, what I want to look at is the limit as x approaches -2, because that's where my horizontal asymptote is going to be, of h of x. And I want to look at it from the left, and I want to look at the limit as x approaches -2 from the right. Okay, but now I'm going to use the exact same trick as I did before. I'm just going to look at the sign of the function. So I'll do that on the side here. So the only places this function can change sign are at -3, where I have an x-intercept, or at -2, where I have a vertical asymptote. So I just need to pick one point on either side of -2, but this is where you need to be careful. I need to be careful that I don't pick something that goes beyond -3. So I'm going to take -2.5. So to the left, what do we have? -2.5 plus 3 is positive, but -2.5 plus 2 is still negative. So that means to the left of -2, the values are negative. So this is going to have to approach -infinity. Whereas if I take something to the right, let's say 0, I've got positive over positive. Here, it's positive to the right of -2. Hence, this is going to be approaching positive infinity. Okay. And that's how I can determine all this information by just recycling what I learned about rational functions in the past. Okay. Whether it's oblique asymptotes, whether it's using the sign of the function, whether it's using how to determine the horizontal asymptotes when the numerator and denominator have the same degree. Okay, any questions on this? No? Okay. So if there's no more questions, I will stop recording.